everyone, and welcome to another episode of Organic Chemistry with Wikipedia. Today we will be talking about the reactions of benzene. So let's get started. All right, so the most common benzene reactions are those of substitution. So we are going to be talking about how to add chlorine, bromine, nitro group, an amino group, and then these two sulfate groups as well onto a benzene ring. All right, so let us begin. Okay, so the first thing we have is halogenation. So halogenation will only occur in the presence of an iron catalyst, and it doesn't occur with all of the halogens. It only occurs with chlorine and bromine. Okay, so if we look at our benzene here, we have benzene, and then let's draw out these, and then we add it to it some bromine. And then we need some sort of iron catalyst. It doesn't really matter what catalyst we use. Normally we use an iron 3 chloride or an iron 3 bromide. It doesn't really make any difference. We'll, for the sake of consistency, just keep it as bromine. All right, and so then what we end up with here is a benzene still, and then one of the hydrogens is replaced with a bromine, and then I produce that hydrogen bromide. And then the same thing happens with chlorine. And we add to it some of this, and then we'll use an iron 3 chloride this time. And then we get our substituted benzene is substituted with chlorine, and then we make some hydrochloric acid or some hydrogen chloride. Okay, so what we're going to do now is we're going to draw out the mechanisms for how this the mechanism for how this happens. So it's a couple-step process. So we'll go through and we'll see exactly how it is that we halogenate our benzene ring. All right, so we'll start off with step 1, obviously. And so the first step is creating something that is electron deficient for the benzene to grab onto. So our bromine is going to, we'll use bromine, is going to grab on to, so our bromine is going to react with our catalyst here. So the electrons are going to join up with the bromine over here, separating itself from the other one. And these electrons are going to reach out to this iron, which is a positive charge because this is an ionic compound. So then what we end up with here is we get a bromine that only has 6 valence electrons, so it is positive. And then we end up with this weird thing here that's this bromine attached to this FeBr3. And then this whole thing here is going to be negative. And so we'll just put a negative sign over that right there. Actually, let's put our negative over our iron, because our bromine is perfectly happy. All right, so now we have this lovely bromine ion, this positive bromine ion. So now that it is a positive ion, our second step is that our benzene is going to reach out and grab that positive thing. So we have benzene here. All right, so our benzene is going to react with this positive bromine. So basically what happens is that this double bond here is just going to reach out and grab hold of that. So we end up with this situation here. All right, so this double bond is no longer, so we end up here with a hydrogen and a bromine. So this carbon ends up being positive because it doesn't have 4 bonds to it. So this hydrogen was already here before, but I'm just drawing that because we're going to need that in the next step. But basically what we've got going on here is that we've taken this double bond and we've swung it out to accommodate this bromine. So now this carbon here has 1, 2, 3, 4 things attached, but this carbon down here, because it no longer has that double bond to pull from, only has 3 things attached. So that's what gives it that positive charge here. So a positively charged benzene ring is called the iridium ion. So what we've made here is an iridium ion. How fun and exciting. Okay, so now we have this positive benzene ring, so we need to get rid of that. So what we're going to do now for our final step, step 3, is we are going to take our positive benzene, or iridium ion. There's nothing there, but there is something there. And then we've got hydrogen coming off of here, and a bromine also coming off of here, and this little dude is positive down here. Okay, so if we recall back up here, we had this fantastic little compound here, this species, as we would call it. So now this species is going to come back around, and we're going to FeBr3. All right, so what we have here now is that this bond, this bond will go back to the iron. These electrons will grab onto that hydrogen. And what we end up with now is our bromobenzene. And these electrons have collapsed back into the double bond here. So we have our double bond intact there. And then we have created some hydrogen bromide. And then, of course, our catalyst is now back intact. So that is our 3-step process on how it is that we brominate benzene. This is the same process that would undergo chlorination, so we could do the same thing, just replacing each of these benzenes with a chlorine instead. So we separate our benzene to create a positive ion and a negative complex ion, and then our benzene attaches itself to the positive bromine to create an iridium ion. And then our complex compound grabs onto that extra H to relieve that iridium ion of the positive charge. And lo and behold, we get our stuff. Hooray and huzzah. Okay, next up. So next thing that we have is what we call nitration. So nitration will occur, we add a nitro group onto our benzene with the, using the two of the three N and two of the three O's from nitric acid, and then we do it in the presence of a sulfuric acid catalyst. So this reaction is kind of cool because you can do it on already substituted benzenes. So like if you already have a chlorobenzene, you can nitrate it and it'll do this exact same thing, and it'll be great. We'll take our benzene ring, and to it we shall add some nitric acid. And we'll do that in the presence of sulfuric acid. And then what we create here is going to be a nitrobenzene plus water. All right, so that's our base reaction here. So let's take a look at the mechanisms that enable that to occur. All right, so again, this is a multi-step process. This is a little bit more complex than the chlorination, or the halogenation, I guess we should say. Oopsies. There we go. Step 1. All right, so step 1 is creating some kind of nitro group here, because if we, look at the HNO3, we want it to be an H, or we want it to be an NO2 that attaches itself to the benzene, so we have to create that first. All right, so we've got here some sulfuric acid, and I'm just going to draw this in a way that can enable us to figure out what's going on here. All right, so we have the sulfuric acid, and then we're going to get some of this nitric acid, and I'm actually going to draw out the structure of nitric acid to help us better kind of see what's going on here. 1, 2, 3, 4, 1, 2, 3, 4, 6. Okay. All right. So here we have this lovely nitric acid hanging out. And so what we're going to do is, first off, we're going to take this oxygen. Oh, I forgot to draw the lone pair here. So we're going to take our oxygen, and our oxygen is going to, what do we have going on here? Our oxygen is going to reach out and grab that hydrogen, and then that bond will absorb itself in here. So what we end up with, we have this HSO4 minus that's from the catalyst. And then we have this guy right here. So we have a double bond, a single bond O that has two H's coming off of it, and it's only got one lone pair now. All right, so when I did this, I ended up with a slightly positive charge over here on here, which is not great. So what we need to do is we need to get rid of that. All right, so this complex guy right here, what we're going to do is, in our next step, our water breaks free from this compound. All right, so we'll just redraw this. We have N, da, 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 and then we have an O, and then we have an O, and an H, and a lone pair, and this is positive. Okay, so how does this process work? So what we've got going on here is that these electrons here are going to move to make a double bond there, and that pushes these electrons to come over to this oxygen and supply that, and now our water has broken free. So here we end up with our water, our product of water, and we end up with this N double bond O, 1, 2, 1, 2, and then this guy overall has a positive charge. So this is our nitronium ion. All right, so now that this has a positive charge, now we are right back where we were with halogenation, where the benzene is going to reach out for this positively charged species. And then the process from here out is exactly the same as the process of halogenation. So we have here a benzene ring, and we have this nitronium ion that has a positive charge. All right, and so our benzene is going to reach out to this nitronium, and what we get is we lose this double bond here, and so there's an H that's already here, but now we have this N double bond O here, and that creates a deficit. So here, this carbon has a complete octet, but this carbon up here, remember there's a hydrogen attached to this, so it has 1, 2, 3 things attached, which means that it is deficient of an electron, and so again we have created this iridium ion. All right, and we'll throw those lone pair on there just for the sake of having it there. All right, so now we need to get rid of the iridium ion. So if we remember way back from up here, this HSO4, so we're going to take our HSO4 now and we're going to use that to remove that excess hydrogen. All right, so we've got here, we've got NO2 and hydrogen, and then we have HSO4 minus. All right, so that HSO4 is going to come out and grab that hydrogen, and these electrons will fall back into that double bond, and we end up with the nitronium double bond intact again, and we have nitro group on here, and then that H2SO4. So we've recreated our catalyst, and then we have this water that we made up here that is left over, and so that's how we get those things. So substituting benzenes is all about creating a species that is electron deficient so that the benzene, the double bond in the benzene will, or not the double bond, but like the bond structure of the benzene is going to want to reach out and grab onto that. Okay, so next up we have the catalytic reduction of nitrobenzenes. So as it turns out, nitrobenzenes are not actually like super duper useful. Well, they are. Like we use it to make TNT, trinitrotoluene, is what we use for explosives. But there is a bigger purpose here, the catalytic reduction of nitrobenzenes. So the catalytic reduction of an alkene results in saturating that double bond. So like if you have CH2, CH2, then adding H2 will saturate that double bond and you just end up with CH3, CH3. All right, so when we talk about the catalytic reduction of alkenes, what we're doing is we're saturating the double bond. When we talk about the reduction of a nitrobenzene, we are not saturating those benzene bonds because it's too stable of a structure. So what ends up happening, and it undergoes the same kind of process, but instead of the hydrogen breaking out to instead of the hydrogens breaking out to remove the double bond, what it does is it actually reduces the nitro group, so it removes the oxygen and replaces it with hydrogen. So instead of NO2, we now have NH2. And so this is the same, I move those rings around. This is the same, and it doesn't really matter how you draw these benzene rings, just as long as they are alternating. This happens under the same circumstances that regular catalytic reduction happens. You need some sort of metal catalyst, platinum, nickel, palladium, and then you need very high pressure. So we throw 3 ATM down here. All right, and then the product of this is actually 2 water molecules that we get from this whole situation here. And we're not going to go into the mechanism of this. This is a bit more complicated. So this is aniline. And so we can use this for creating aminobenzenes, which have a lot of uses in nature. Okay, so that is what we can do with nitrobenzenes. All right, next up we have sulfonation. So if you heat an arene with some concentrated sulfuric acid, you produce what's called arene sulfonic acids. So an aromatic sulfonic acid is comparable in strength to sulfuric acid, so it's a pretty strong guy that we're looking at here. All right, so how does this work? So this is going to be, I'm going to take a benzene ring, and I add to it some sulfuric acid. There we go. So we add to it some sulfuric acid, and we end up getting is a diagram. You think I'd be better at drawing benzene molecules by now. We end up getting this lovely creature here, and then we make some water as well. Okay. All right, so let's take a look at the mechanism for sulfonation. So the first part of this, step 1, is we are going to take 2 of these sulfuric acid molecules. And what we're going to find is that in the reaction, only one of them is consumed. The other one is going to be remade, so it serves as a catalyst. All right, so when we do this, we get some sulfur trioxide and some hydronium and this HSO4 minus. All right. So what's going to happen next is the benzene actually is going to reach out for the sulfur trioxide. In a lovely twist of events here, we end up with the benzene reaching. So sulfur trioxide looks like this. All right, so this benzene is going to reach out and grab a hold of that there, which pushes this set of electrons back onto that oxygen. And what we end up with is the iridium ion again. So there's a deficit here, and we have an H here, and then we have this S, and then one of our O's, just for the sake of symmetry, I'm just going to rearrange this a little bit. One of our O's got lost its double bond, and so now it has an overall negative charge. And then my iridium up here, my carbon has a positive charge. All right, so now I've got this whole situation going on here. All right, so now that I have this base model, we're going to rearrange some stuff to get something that is significantly more stable. All right, so here we have kind of the same thing that we do every single time we're substituting, where we got to get rid of this H to create that stability on the iridium. All right, so we're going to pull this HSO4 from up here. There's not two of them, there's only one of them. HSO4 minus. All right, so we're going to do that, and then our HSO4 is going to pull this hydrogen, and then that double bond is going to go back. And so we end up with double bonds and just an SO. And then we got rid of the positive charge here by folding back that double bond, but this oxygen here is still negative. So it's an H2SO4. All right, so we got to do something about this negative. All right, so if you remember from up here, we made the HSO4 and we dealt with this HSO4 minus, and then we dealt with this SO3, but we still have that hydronium that's left there. Right, so that hydronium is going to come back and it is going to take care of that negative charge on the oxygen by stealing away, you guessed it, the hydrogen. All right, so we've got, this is complete. So we have S double bond O, single bond O, and it is negative. And then we take our hydronium here, or H3O plus, and the electrons here come by and steal one of those hydrogens. And so we end up with this lovely benzene sulfonic acid. So it goes now double bond, single bond OH, double bond. And everybody is happy, and we get some water out of the deal as well. All right, so that is how we make our benzene sulfonic acid, which is what this lovely this lovely molecule here is. And you can see it's got 3 O's and an H, which is why it is SO3H. And then these sulfonic acids are really useful because through a set of events, what you can do now is, so you have this OH group here, what you can do is you can actually replace that H with a sodium to create a detergent. And we're not going to go through the mechanism of all of that, but to give you an example, we have CH3, CH2, 10, CH2, and that is attached to this lovely benzene ring here. And in the first step, so this is a two-step process. So in the first step, what we're going to do is we're going to add that sulfuric acid to sulfonate. And then in the second step, we add the NaOH. And what that does is it creates this right here. So we get CH3, CH2, 10, CH2, and then we have this benzene ring, and it's SO3, which has an overall negative charge, and an Na that has a positive charge. So we write it like this because now this is a salt. So we have the negative portion of the salt is all of this organic stuff, and the positive portion of that salt is that Na over there. And so what this does is this is a detergent that we can use to clean stuff. And this detergent here is called SDS. So what we've done is we've taken that acid and we've neutralized it with a base to create a salt. And this is SDS is a common detergent that is used in household products. Okay, so this has been another episode of Chemistry with Wikipedia, Organic Edition. I hope you learned something, and until next time, keep on chemin'.